For the last section in this module, we're not quite finished with chapter 10, we're only halfway through, but this is the last section in this module. We're going to look at the idea of absolute convergence and then two more tests for convergence, the ratio and the root tests. Now, sometimes you have a series where you've got some terms positive and some terms negative, and in those cases your series may converge, it may not converge. What you might want to check, is whether the absolute values, the series of absolute values of those terms converges. And if the series of absolute values converges, we say that a series converges absolutely, because we're looking at the series of absolute values. And if the series of absolute values converges, then we can say that the underlying series also converges. Now, not all convergent series will converge absolutely, so you do need to be careful of that, but all series that converge absolutely will also converge. So the first test that we have here to see if a series converges absolutely is called the ratio test. And in the ratio test, we're going to look at the limit as n approaches infinity of the term a sub n plus 1, and we're going to compare it to the term a sub n. And we're looking at the absolute value of these two terms, so everything here is going to be positive. And we're going to look at what that limit equals. There, it almost looks like a p, but it's actually the Greek letter rho. And if that value rho is less than 1, we say that the series converges absolutely. If rho is greater than 1, the series diverges. If rho is equal to 1, the test is inconclusive, and we need to look at another way to test if that series converges or not. So I'm going to go through a couple examples of this with you. The first one here says use the ratio test to determine if each series converges or diverges. So we're given the series that sums from n equals 1 to infinity of 2 to the n over n factorial. So I'm going to look at the limit. Oops, there we go. As n goes to infinity, and we're going to look at the absolute value of the n plus first term over the nth term. So that's going to be 2 to the n plus 1 power over n plus 1 factorial. And we're going to look at that over the nth term, which is 2 to the nth over n factorial. Now for this one, I'm going to do a couple things here. First, I can go ahead and drop my absolute value bars because all the terms are going to be positive here. Also, I'm going to rewrite this as a multiplication problem, and I'm going to do a third thing at the same time. I'm going to rewrite the 2 to the n plus 1 and the n plus 1 factorial. So we're going to do a whole bunch of things all at once there. So we're now looking at the limit as n approaches infinity. So up here, 2 to the n plus 1 is 2 to the n times 2. N plus 1 factorial, I could write that as n plus 1 times n factorial. And then the denominator is going to be n factorial over 2 to the n, because we flip it. Now I can start to cancel here. The 2 to the n's are going to go, and also the n factorials. So I'm left with just 2 over n plus 1. The limit as n goes to infinity is going to be 2 over infinity, which is 0. So in this case, rho is equal to 0. Well, that's definitely less than 1, so the series converges absolutely. And since the series converges absolutely, it also converges. So let's look at another example. Here I've got the series from n equals 1 to infinity, n to the square root of 2 power over 2 to the n power. So we're going to do the same process. We're going to look at the ratio test. So it's the limit as n approaches infinity. I'm going to look at n plus 1 term. So it's going to be n plus 1 to the square root of 2 power over 2 to the n plus 1. And we'll compare it with the nth term, which is what we just have here. Now, just like I did before, I'm going to rewrite this. It's actually, I forgot something. It's actually the absolute value of all this. Forgot something kind of important there. However, I will be able to drop those absolute value bars because all of our terms here are going to be positive. But when I rewrite this, I'm going to rewrite this one as a multiplication. So I've got n plus 1 to the square root of 2 power over the 2 to the n plus 1. I'm going to write as 2 to the n times 2. And then we'll flip the denominator, so we have 2 to the n over n to the square root of 2 power. The 2 to the n's are going to cancel. So what I'm left with, n plus 1 to the square root of 2 over 2 times n to the square root of 2. I'm going to rewrite this a little bit. What I'm going to do is write the limit as n approaches infinity, and that 2 in the denominator I'm going to pull out as a 1/2. And then n plus 1 to the square root of 2 over n to the square root of 2. I'm going to write that as a single fraction raised to the square root of 2 power. So that's n plus 1 over n to the square root of 2. Now, that single fraction I can then break up. So I've got the limit as n goes to infinity of 1/2 times 1 plus 1 over n to the square root of 2 power. As n goes to infinity, 1 over n goes to 0. So I have 1 raised to the square root of 2 power. Well, 1 to the square root of 2 power is still 1. So I've got 1/2 times 1. So that limit there is 1/2. Since that's my row value, and since that is less than 1, this series also converges absolutely. And we're going to look at one more of these just to run through the process. For the third one here, we are given the series from n equals 1 to infinity of n factorial over 2n plus 1 factorial. So let me set it up one more time. We've got the limit as n goes to infinity. We've got our absolute value bars. So I'm going to look at the n plus first term. So that's going to be n plus 1 factorial. In the denominator, I've got 2 times n plus 1 plus 1. So the 2 times n plus 1 is 2n plus 2 plus 1. So we get 2n plus 3 in total down there. And that's going to be over the nth term. Once again, all of these values are going to be positive. Our n values are all positive, so will these be. I'm going to rewrite this as a multiplication. And at the same time, I'm going to rewrite the factorials here. So n plus 1 factorial, I'll just do n plus 1 times n factorial. 2n plus 3 factorial is going to be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And then again, the denominator, we'll go ahead and flip it upside down. So we have 2n plus 1 factorial over n factorial. So I can go ahead and cancel a few things. So what I'm left with is n plus 1 over 2n plus 3 times 2n plus 2. 2n plus 2 is just 2 times the quantity n plus 1. So I've got a few more things that I can cancel. Those n plus 1s are going to cancel. So we're just left with 1 over 4n plus 6, which I'll go ahead and rewrite. Well, as n goes to infinity, this denominator also goes to infinity. So 1 over infinity, that's going to go to 0. So our rho value now is 0. That is certainly less than 1. So once again, the series converges absolutely. So that is the ratio test. In the second video, I'm going to go over another test in the section called the root test.